Question 3. A disk has a total charge of 500 pi microcoulombs that is uniformly distributed over the circular disk with the following limits. So the radius of the disk is 5 meters. So the disk cover distance from 0 to 5. And Z is equal to 0 meters. So this is sitting on an XY plane. And you're asked to calculate the force on a point charge of 500 microcoulombs sitting at 0.005 meter as shown in the figure. Okay, so because you're given this, so it's best to solve this in a cylindrical coordinate systems. Okay, so we want to define an area on the disk, or a small area on the disk, call it dA. So in cylindrical coordinates, okay, so if I redraw this, so we want to define a small change in the area, call it dA. Okay, so if this is r, so this distance here is dr. And this, if I call this phi, this small angle here is d phi. And therefore, this small change of distance here is r d phi. And therefore, this area here, dA, is equals to r dr d phi. And that's how we have this in our dq. Okay, so our dq, so this is basically our dA. So our change in the charge is the surface charge density times the small change in the area dA. And dA in a cylindrical coordinate is equals to r dr d phi. And this is how this come about. So this is x, y, and z. And then we can define any point in our cylindrical coordinate as a radial, and then our angle, or our azimuth angle, and then z. And then we can define any point in our cylindrical coordinate systems. Okay, so in this case, you're given the total charge is 500 pi microcoulombs, but you're not given what is the surface charge density, but what you're given is that this charge is uniformly distributed over the disk. So the disk area, so this disk has an area of pi r squared. And the radius of the circle is given as 5 meters, so this is pi 5 squared. And therefore we can now define the charge density, or the surface charge density, rho s is equals to 500 pi divided by pi 5 squared, and that gives us 20 microcoulombs per meter squared. Next, we can define the vector r. Okay, so our vector r, so we have, so in our vector r, here, vector r, so this is our vector, this vector here. This vector is the vector positions of 0, 0, 5. And this point on our small disk here. So here we have a vector position here, which is r, 0, 0. And because we want the vector r, so that will be the negative of this vector plus our 0, 0, 5. So therefore we can define our vector r as zero, 0, 5 minus our r, 0, 0. Okay, so the small little disk vector position is a variable. It's changing with r. So this small disk here could be here, could be here, could be anywhere around on that disk. Okay, so we don't specify exactly what r is, but r is just a variable. But it's sitting in the xy plane where z is equals to 0. Okay, and then so it's sufficient just defining it at r equals to anywhere along the radial directions. So this equals to minus r, 0, 5. And then the unit vector of this divided by this magnitude. The magnitudes will be r squared plus 5 squared. So this is the differential charge. This equals to dq equals to the surface charge density r dr d phi. So with that we can work out the differential force due to the differential charge on the disk. Okay, so we can write down dF by applying Coulomb's law. That will be Q, which is the charge at 0, 0, 5 times the differential charge which is rho s r dr d phi divided by 4 pi epsilon naught the magnitude of our vector r squared times our unit vector of our vector r. Okay, so putting all the value of differential force equals to 500 microcoulombs times 20 microcoulombs per meters times dA, which is R dr d phi, over 4 pi. Epsilon naught is 8.854 times 10 to the minus 12. And then our magnitude of R is root of R squared plus 5 squared. Square of that gives us R plus 25. And our unit vector is minus R 0, 5 over square root of R squared plus 25. Okay, so this gives us 9 minus R 0, 5 over. So this value here times the square root of this will give us R squared plus 25, 3 over 2. That's our R dr d phi. Therefore, the total force on the charge due to the whole disk is F. So the top equation here is due to that differential charge. So if due to the whole disk, we have to sum up or integrate from R equals to 0 to 5. And then angle going from 0 to 2 pi. That will account for the whole disk. 9 minus R 0, 5 over R squared plus 25, 3 over 2 R dr d phi. So we can see that it has an R component and a Z component, but due to the symmetrical of the disk, we know that the force in the radial directions, i.e. in the A sub R in the radial directions, so the force in this directions will cancel out. Okay, so means that if I have a charge due to this point here, there is a counter charge that counter out at that point. So as a result, we know that the force is only in the Z directions. Okay, so meaning that if I take, let's say, well, let me re-explain that. So if I have a point here that gives rise to a charge, give rise to a force, that point in that directions, so then I'll have a charge in the opposite direction of the disk that gives rise to another charge in the opposite direction to counter out that force. Okay, so So the only force that results will be the force. So meaning that I'll have a force here and I have a force here. So as I resolve this into our radial components, these two will counteract. So in other words, we do not need to consider our radial components. Okay, we can simplify our calculations into F equals to the integral of r equals to 0 to 5, and then integral phi to 0 to pi, and we are only interested in the radial, not only interested in the z direction. This will be equals to 9 times 5 times r dr d phi over r squared plus 25 3 over 2, to show that we are only working on the z direction, so multiply this by our unit vector z. So this equals to 45 integral of 0 to 5 for r dr over r squared plus 25 to the power of 3 over 2, and then integral 0 to 2 pi d phi, and our unit vector z. It's 45 integral of r over r squared plus 25 3 over 2. This will give us minus 1 over r squared plus 25 1 over 2. This over limit 0 to 5, and this integral here simply gives us 2 pi. And then don't forget our unit vector z, just to show that it is in the z direction. Okay, so solve this. We give us (16.56) z Newton, or in our coordinate point of vector, which is 0, 0, 16.56 Newton. Okay, so the force in the x and y direction is 0, so the force is only in the z directions, which is 16.56 Newton. So there's the solutions to this. So the force at this point here would be 16.56 Newton going upwards if you have a point charge of 50 microcoulombs at that point.